This little clip here will be about the mechanism of acyl substitution under basic conditions. This is a much simpler, shorter mechanism than under acidic conditions, and it's essentially what we had gone over on the bottom of the pink sheet. But if you have basic conditions where you have a strong base in solution, then you cannot have any protonated or positively charged organic species. So everything needs to be either neutral or negative charge. And as you'll see, it's much simpler, shorter mechanism than the acid catalyzed one. So let's get started here. We have a carboxylic acid anhydride as our electrophile. Here's either one of these carbonyls we can use as our electrophilic carbonyl, and then we have our nucleophile here, which is a strong base and good nucleophile. So first thing that happens is that the nucleophile comes in, adds to the carbonyl, breaks the pi bond, and as it does that, it puts a lone pair and a negative charge onto the oxygen. We have not kicked out a leaving group yet, but we have added our nucleophile. And as you see, every single atom here is either neutral or has a negative charge. So this is an equilibrium reaction. It can go forward and backwards, and going in this forward direction, as we already said, this is an addition of reaction. So what is left to be done to get to our final product here? We have to kick out a leaving group, and if we kick this leaving group out, it will be kicked out as a negative charge, which is exactly what you want in a basic solution. And as we reform the pi bond and kick out that leaving group, then we end up forming this final product here in an elimination reaction, reforming the carbonyl. So we're kicking out the leaving group, negative charge here, and then the sodium ion is the counter ion there. So again, the one intermediate in this reaction has no positive charges on it. It has one negative charge on it, and then the product, the kicked out leaving group, has that negative charge. Pretty simple, pretty straightforward.